All right. So I just remembered to click record, so sorry for the folks at home. Pause right now and look at this. If you're looking at this at home, pause right now and write this down. And now if you're back, pause this right here and write this down. And we'll talk more about this in class. That is not bad. Usually I'm used to just having both periods, but we had that doctor's appointment this morning. So pause here, write some things down to make sure you get it. I know there's a lot going on here. But we'll talk more about it. And you'll see it on the homework that I sent out last night that really isn't due until Sunday. So you have some time to work on that, and we can talk about that this weekend if you have anything. Okay, so what I wanted to do was kind of build on that table that we started to create comparing different degrees. So looking at multiplicities. Oh, yeah. Multiplicity. That says multiplicity. And comparing like the degree to what the shape of the graph is going to look like at that spot. Okay, and we looked at what happened when we had degree 1, when we had degree 2, and when we had degree 3. But I want to keep going. I want to look at what happens with 4, 5, and just so you know, this list can keep going. But if you know it up to here, you'll be able to tell the difference between a 6 and a 7, or a 6 and a 12, whatever the case may be. Okay. If it's 1, it's just linear, right? Where we cross right through that x-intercept like a line. So the blue dot is going to be my x-intercept. Okay. So we saw that one. For a degree 2 term, it could be like that, or it could be like that, where the x-intercept is that vertex, that turning point of that. So when it's an odd degree like this, so far 1, if it's an odd degree, it's going to cross the x-axis. It's going to cut through it. It's going to keep going, right? If it's an even degree, it's just going to touch the x-axis and go back the way it came. Whether it's coming from the top, it's going to bounce back up and come to the top. Or if it's coming from the bottom, it's going to come back up, hit the x-axis, and then head back down. It is going to just touch. Or you could say it bounces off. It's going to touch, or it's going to bounce off the x-axis and head back in the direction that it came. Okay, so just knowing that can help us really make sure that these more challenging graphs that we're going to do get a whole bunch easier. Okay, if it's a degree 3, it's going to look cubic at that spot. Right, so maybe it's coming from the top, or maybe it's coming from the bottom, but it's right in the middle, right there, at that bend. That's where that x-intercept is going to be, and you want it to try to be relatively symmetric on either side, as best you can. Okay, and what I want to do now is I just want to I'm going to share my screen. I want to go back to Desmos and look at the calculator and compare something like a degree 2 term at a specific x-intercept to a degree 4, to a degree 6, to a degree 12, whatever it happens to be. Okay, so let me present real quick. I'll jump back into Desmos because it's super fast and easy to type. Just make sure. Okay, good. Present. Awesome. All right, so take a look at this. Let's compare what happens at like x minus 1 squared. And what happens if I start messing with higher and higher degrees? I'm going to just zoom in relatively close to that spot so we can see what happens. What if it was x minus 1 to the 4th? Do they still have the same x-intercept? Absolutely, right? Because that factor is still x minus 1. It's just happening a different number of times. Maybe I have that factor twice compared to having it 4 times. And what I want you to notice is that although the x-intercept is still the same, the way that we approach the x-axis at that spot happens a lot faster. So if you look at the red graph here, we're coming down. You know, I'm going to turn this one off just for a second. You know, come down and we don't really get all that close to the x-axis until we really get close to 1, and then we just bounce off and we head back up, right? It's even, so it's just going to touch or bounce off the x-axis at that spot. But if I bring back that x minus 1 to the 4th, look how much faster it comes down to the x-axis, right? I get really close to the x-axis. I'm going to zoom in even more. I get really close to the x-axis a lot faster, and I spend more time like hugging the x-axis as I do those graphs. And especially for us, since we're just doing these kind of relatively small sketches, right, nearby, we really want to exaggerate the difference between something like x minus 1 squared and x minus 4 squared. And I mean, even something like x minus 1 to the 6th. I get rid of that little subscript somewhere, right? Take a look at the red graph compared to the green graph and the blue one in between. Like from the red to the blue to the green, we come down faster the higher the exponent, and we spend more time near the x-axis when we do that, okay? And so when you've got these even exponents, okay, so 4s and 6s, okay, when you've got an even exponent, what you're going to see is something called flattening. Okay. As n gets, I'm not going to say n because I'm just talking about the degree of that piece. As the multiplicity increases, goes up, the graph gets flatter as it approaches that x-intercept. Okay, so we've got this thing called flattening. Okay, so degree 4 compared to degree 6, degree 4 compared to degree 8, compared to degree 10, right? It just gets flatter and flatter and flatter, and it spends more time near the x-axis. It comes down and almost creates this like the bottom of a container. It's got this like, comes down real fast and then flattens out. And look what happens when I make it 100. X minus 1 to the 100th power, it's almost completely vertical when you get not even all that far away from the number 1, because you've got these numbers getting bigger up to the 100th power. And I mean, let's make it 1,000. It's almost square, right? It's almost got a perpendicular angle at that spot because things are getting so big. 1,000, 10,000, a million, you can't even tell the difference right now because that number is so big. But as I get from 100 to 10, right, big difference, 100, 10, 100, 10. Okay. So what I want us to be kind of comfortable doing is taking a look at something like degree 2 and comparing it to something like degree 4, and I'm going to exaggerate. Okay, I'm really going to like come up fast, approach the x-axis, hug the x-axis, and as symmetrically as I can, so I'm going to put that x-intercept right in the middle, put this one right in the middle. I want to be able to visually, even though that's not really quite as flat as it needs to be, show a big difference between a power of 2 compared to a power of 4. Okay? Or a power of 2 compared to a power of 6. It's kind of hard for us to really navigate 4s compared to 6s when we're just sketching relatively small graphs. Or like 5s to 7s, we'll talk about these odd multiplicities too. But that's kind of a big difference that I'd like to see. I want to see the difference between that and that. And I want you to look at a graph that you're sketching and say, I've done a good job at flattening out a degree 4, like a multiplicity of 4 factor compared to multiplicity of 2. Okay? And similar things are going to happen with x to the 3rd compared to x to the 5th. And that's all I have to do is change these. Okay, x to the 3rd, x to the 5th. Okay, now if it was just plain old x minus 1, and it was just a degree 1, so I wonder if I can reorder these. Let's see. Slide this one up. Yeah, nice. Okay, so the green one, this is linear, right? Just goes right through it. And if that was just the whole function, then it's just a line. But if that's just that factor, then me zooming in to just basically a box or 2 on either side, and probably even closer than that, right? Maybe less than a tick mark on either side. We just want it to look relatively linear when we do that drawing. But when we get to from degree 1 to degree 3, you can see that graph in red, and I'm going to zoom in to really magnify what's happening there. Now we're just literally less than one box on either side. There's a big, big difference from the green graph to the red graph. The red graph goes up much faster, but as it approaches that x-intercept, it doesn't flatten out because I'm not going to head back up in the direction it came. We call that something else. When you've got these odd multiplicities and they're bigger than 1, we have what's called flexing. Okay, it is, and that's the technical mathematical term, just like flattening is relatively technical in the way that we talk about it. It's just flexing. It's just like it just kind of does what, if I said to flex, what you would do with that. It flexes at that point, but because it's odd, it's still going to cross through it. But compare that red one now to the blue one. Right? The blue one, higher degree, comes up faster. It gets closer to the x-axis sooner, and it spends more time along the x-axis. And so I'm going to really exaggerate that flexing here. I'm going to spend a lot of time at the x-axis in that space. And whether I'm coming up from the bottom or I'm coming down from the top, I really want to exaggerate how long that graph spent, and I just try to be balanced. I try to put the x-intercept relatively close to the middle of that flexing zone. Okay? And although this list keeps going, we're not. I'm good. 1 through 5 is what I need. Okay? 6 and 4 are going to look so similar when we sketch them by hand. And if we had the graphing calculator, then we could really get it. And if we had graphs that were this big, right? If I was actually graphing in a space that was as big as this projector, then we could do some things to tell the difference between a 4 and a 6, or a 6 and an 8. But for me, these are enough. Okay, 1 through 5. Those are the multiplicities that I want you to be able to graph for me, take a look at them, and make sure that when we do the graphing, that we can tell the difference between 1 multiplicity and 3, between a 3 multiplicity and a 5, and from a 2 to a 4. Right? Maybe you've seen that before, maybe you haven't, but now that you've got it, now you've got it. Okay, so this is a really nice one single space for you to look at, to go back to a nice little chart that will help you tell the difference between one kind of multiplicity and another. Okay, but with our last thing, and then I'll let you go, I wanted to do one much higher degree polynomial graph by hand. Okay, so I'm going to give myself actually some graph paper to look at. It's going to help me do some graphing a little bit easier. Okay, but I want to make up a function that's going to do what we want. But let me give myself some axes too. So if you're at home watching this, you don't have to use graph paper to do it, but give yourself a set of axes. Let's see how accurate this thing's going to be. But make it a little bit larger than we have in the past. I'm going to go a bunch of tick marks in either direction. Probably at, let's go, if we can, let's go like -10 to 10. Make it relatively wide. Okay, the up and down isn't so crucial because our y-intercept could be anywhere and we just make our own y scale. But I want to make every box here all worth 1. All right, so I got all these tick marks and all of these are going to be worth 1. Okay, I'm going to throw some arrows at the ends. Now I'm just putting the tick marks for good measure. You don't really need to draw those in there. But I'm just doing this one. Labels, x. And let's say this is some polynomial function. So I'm going to call it p of x for polynomial, but I haven't given it to you yet. Every box is worth. What I wanted to do is I wanted to give you kind of a big, higher degree polynomial function, but the higher the degree is, the harder it can be to factor. So if I have a degree 3 or degree 2 or a 5, and maybe it has a greatest common factor, well, that can help, right? That can make things a whole bunch easier. But what if it's just a bunch of different factors with a bunch of different multiplicities, like an x minus 7 to the 3rd, an x minus 2 to the 5th, and an x plus 3. Like if you have all of these factors, and it's written out the long way in standard form. It says degree 15, and it's written something x to the 15th plus something else x to the 14th plus something else x to the 13th, and you've got 16 terms in there. The factoring is just mind-numbing. It would take forever. So sometimes what we'll do is when we write functions, so p of x, instead of writing it in standard form, we can write them already factored. And usually that's what we'll do when our functions are much higher degree. So let's say we've got, I don't know, like 1, 2, 3. Let's say we have like 4 different functions, 4 different factors. Right? I don't know, x plus 7 times x plus 2 to the 3rd, x minus 1 squared, and x minus 6 to the 4th. Let's say that was our function. Before we can do any of this plotting stuff, and plotting x-intercepts, and getting a y-intercept, and talking about end behavior, we have to know what we're looking at first. Okay, and I'm not sure if you saw this or not last year with higher degree polynomials where things are already factored. So if you haven't, this is going to be some new stuff, and it's going to be a little bit different than what it looks like when it's in standard form. Okay, I'm going to stop sharing, so really the only screen you have to look at is the camera. So, okay. I want to hear from you. What is the degree of a function when it's factored? Now, to answer that question, think about what would happen if we multiplied this whole thing out. Because when it's multiplied out and you see the whole thing, then it's just the largest exponent.
Add up all the exponents.
Perfect, right? Because if I were to multiply this thing out, well, there's nothing there. But this thing, I would eventually have an x cubed. And I would eventually have an x squared. And I would eventually have an x to the 4th power. And so now I have an x times an x cubed times an x squared times an x to the 4th at some point during that multiplication. And so when you've got a factored polynomial, when it's written out this way, your degree is the sum of the exponents. It's not the largest one. We have to add them all up. So we've got 1 plus 3 plus 2 plus 4, 4 plus 6 is 10. Okay, your degree here is actually 10, which is even, so now I can figure out what my end behavior is. Okay, what is your leading coefficient? Well, there's a 1 right here, right? So it's definitely at least 1. But just like with degree where we add up all the exponents, what I need to keep track of is every single leading coefficient to each of those powers. So I really have a 1 times a 1 times a 1 to the 3rd times a 1 squared times a 1 to the 4th. And all of those all together are just 1. But if I made this a 2, and I put like 3x plus 2 to the 3rd, or negative 2x minus 1 squared, that's going to change what that a sub n is going to actually end up being. So we got to be really, really careful when we've got these factored versions of polynomials. Good, so even degree, positive leading coefficient. So I know my end behavior is going to be up, up. So that's a good start. Okay, where's the y-intercept? What happens if you drop in 0 everywhere? Well, let's do it. Okay, so there's 0, so this is just 7. Okay, so I've got, let's do a little work down here. So I've got, okay, 1 for that leading coefficient times 7. Okay, so there's my 1 times 7. Okay, now I got a 0 here. So the only thing that's left in that factor is a 2, but it still has a power of 3. So this is really times 2 to the 3rd. And then do it again, drop in a 0 right here. Okay, so it's 0. So 0 minus 1, so negative 1. But that's negative 1 squared. And then put a 0 right there. Okay, 0 minus 6, negative 6. So negative 6 to the 4th. There's no way that I'm going to do that by hand. I'm definitely going to let the calculator do some of that calculation for me. 1 times 7 times 2 to the 3rd times 1, right, because that's negative 1 squared, times negative 6 to the 4th, which is the same as 6 to the 4th. And amazingly enough, the higher, maybe it's not all that amazing, but the higher degree polynomials you've got and the bigger these numbers start to get, your x values might be nice, but the y-intercept that we get, 72,576. That is how big this y-intercept is going to be. So if you tried to graph this in your graphing calculator in a regular window, it's not going to look the way that we're going to sketch this. Because what I'm going to do is I'm going to pick a spot on this graph. It's positive, so I'm going to put it up there. And I'm going to say, hey, that spot is 72,576. When I mark off the y-intercept, I'm just going to plot it somewhere nice for me. Okay, so I know I've got a point right there for sure. And you can put it anywhere above the x-axis that fits in your graph because it's the only y value that matters. Because the only other points we're going to plot are the x-intercepts. Okay, and so take a look at these factors. The reason that we have it in this factored form that makes it so nice is it's really easy to tell where those x-intercepts are going to be that's going to create a y value of 0. So take a look at this factor right here, x plus 7. If that factor by itself was set equal to 0, where would your x-intercepts be?
Negative
7.
seven.
Just the opposite, right? So I'm going to go negative 1, 2, 3, 4, 5, 6, negative 7. There's a point. What about x plus 2? Set that one equal to 0. Yeah, you just subtract 2 on both sides. I've got another x-intercept right there, negative 2. And then you've got this factor of x minus 1. If I was just looking at that one, right, and I set that thing equal to 0, I'd add 1 on both sides, and I would get 1. And the same thing with x minus 6. If I drop a 6 right there, I'm going to get 0, and there's my x-intercept. So 1, 2, 3, 4, 5, 6. And so I've got a degree 10, but I only have 4 x-intercepts because there are 4 unique factors, right? This one gets repeated 4 times. This one gets repeated twice. This one gets repeated 3 times. And we're going to see that in the way we run into the x-axis, okay? So how do we graph these? Number 1, set up my axes, done. Number 2, plot my intercepts. Did it, right? And the only one that was really kind of crazy was the y-intercept, but because our y scale can be whatever we want, put it someplace nice. Okay, put it someplace that's going to flow nicely with your graph. And maybe you don't even plot that y-intercept. You just connect the graph the way it should, and then you mark it off. That's up to you, right? As long as your end result looks good, I'm good with that. Okay, now I need to draw in the arrows, okay? And we figured that out because the degree was 10, I added up all the exponents when it's factored. And my leading coefficient was 1 because 1 times 1 times 1 to the 3rd times 1 squared times 1 to the 4th. It's just 1, so I know that I'm going to be going up. So here I am to the left of that leftmost one. I don't know, I come up here somewhere and I put my arrow. And then I go over here to my rightmost point, whatever it happens to be. It happens to be this one. At a box or 2 on the outside, I kick my arrows up just to give me a good sense for if I'm doing this right. If I can connect now from left to right, considering the multiplicity of each of these zeros, then I feel really good about what I've got. And when we get to class, I'll show you how to manipulate your calculator to help you see whether or not you're doing this right. But now here we go. I'm just going to connect this thing from left to right. And so I know I got to come down to this x-intercept, but I want to think, before I even get close, what is the multiplicity of that 0? What is the degree of that factor that got me there? Well, if it's just x plus 7, that's x plus 7 to the 1st. So I'm going to, I know it should be connected nicer. I'm going to cut right through it just like a line. Okay, let's say that I did a perfect job. Okay. If you make a mistake, just erase what you don't want. Ta-da, now it looks better. Okay. Now, I have to turn somewhere, right? And I don't know where that is. And my scale is crazy because now every, 4 boxes was 72,000. So usually I just kind of follow whatever is comfortable, whatever kind of flow I have, and I turn around the middle somewhere. But I want to kind of consider, before I get too close to the x-axis, what the multiplicity is at that spot. Because when I think back to this setup, if I have to get to the x-axis really soon, I want to do that. If I have to flex or flatten out because I'm degree 4 or degree 5, I want to make sure that I can show whoever's looking at this that a factor like degree 2 and a factor like degree 4 are going to look very different, exaggeratedly so, okay? And so here I am getting close to the negative 2x intercept, which came from this factor, which has a multiplicity of 3. And so when I connect this graph and I go through that, I have to cut through it like a cubic. So when I take this turn, I have to get up to the x-axis a little sooner than I did with the degree 1. I get pretty close to it, and I flex, and I cut through. Okay. Now, if that was a little bit more symmetric, it would look better. So I'm going to back up and try that. When I do this, I want to really be as relatively symmetric on either side of this graph so that I'm doing a good job at sketching. And that looks a little bit better. Okay? Now, I have another x-intercept that I have to get back to, but I know I have to take a turn somewhere, but we don't know that it's going to happen at the y-intercept. Now, you can use that as your turning point if you want, but it might happen up here. We don't know without calculus, and that's okay. So turn wherever is comfortable for you in terms of the way that your graph flows. But now I've got to come down to this x-intercept that came from this factor that has this multiplicity. And so you see, although these graphs are continuous, I am picking up my pencil constantly to stop and pause and look back. All right, so degree 2, so I have to hit it like a parabola. So I'm just going to come down and bounce back off. If it's relatively symmetric, then you know you did a good job. Okay, and then the last one at x equals 6 came from a factor of x minus 6, and that's got degree 4. And so when I look back at degree 4 compared to degree 2, the things that are highlighted here, I really want whoever's reading this to see that visual difference, that flattening that happens at that spot. I want to exaggerate that, which means I need to take a turn, but I got to get back to the x-axis sometime really early, like maybe a box early. And I'm going to stay along the x-axis for the same amount of time. That was my last x-intercept, and up I go. Okay, so I just wanted to run through that one with you because it comes up on the homework for this weekend. There was one like this where it's factored, and now you've got a couple ideas on how to figure out what the degree is, how to find that leading coefficient, because then you can figure out your end behavior. The y-intercept is the product of your constants to their exponents, which could be a big number. But you can set up your y-scale however you want. Okay, so just, I think, practicing with that homework 2.2b, you're looking at just end behavior, y-intercept, x-intercepts, and drawing some sketches. Okay, it's past 7:35 or 11:35, so I will send you on your way. Thanks, everybody. Have a good weekend. Cohort B, you do not have to log in on Monday. I will have some work for you to look at. Okay, so check Canvas on Monday. Thanks, everybody. Have a good weekend. Thanks for coming. I appreciate it.
Thank you.
Thank you.